So today's session is about quantum computing as such, where we are. I believe you heard about it, but maybe it's still an area you are not focusing on. So before we start, I'd like to give you some messages about what will not be covered. In other words, these are other areas related to IT, which are also quantum related. So we will not cover quantum communication, quantum crypto, post-quantum crypto, and all these are very interesting topics, obviously. And if there is one thing what I like to achieve is not maybe for you to learn a lot about quantum, but to learn about what you have to learn about quantum. By the way, we are in Ostrava, so let's celebrate, because soon there will be a first quantum computer in Czech Republic, and it will be here in Ostrava. And now let's talk a bit about the motivation. Why we are talking about quantum computing, why Arikoma investing in quantum computing, and why we should have an eye open on quantum computing technologies. Well, money matters, right? So there is also a motivation here. What I like to pick up from this slide is the global spending, which is estimated to be around 40 billion, and then the participation of Europe, which is not that high, and the participation of the US and China. I believe these three numbers will deliver the message. But what's important, this is an interesting area, and a lot of companies and countries are investing in this area. Now, the other motivation on the left side, we are so excited about the success of AI, about the high performance computing. However, we believe that the quantum computing can be the last particle in that puzzle, which can then move the AI to the next level. And on the right side, for you who are familiar with the theory of complexity of the problems, let me just quickly summarize that quantum computers of the future will be able to solve problems which classical computers will not be able to solve in a reasonable time or even never. So that's quite a high motivation. The other one, all the major players in IT in terms of hardware or public cloud you see are investing in these technologies. So obviously it's good to follow what folks at IBM, AWS, Microsoft, Google, and others, maybe not that much known for you, are doing in this area. So let's discuss a bit where we are as of today in terms of quantum computing. So, as I put in the title, it's a competition between scientists, technologies, and modalities. By modalities, I mean a physical medium on top of which the quantum computer is built. So, obviously, a quantum computer is using the different phenomena of quantum mechanics or quantum physics. However, different vendors decided to use different modalities. So, the kind of most successful ones, as of today at least, superconducting. Then we see, of course, photonics, especially in terms of quantum communication, trapped ions, and so on. The table on the right side, I believe the second line and first line are the most important as of now. So the first one is number of qubits. Qubit means a quantum bit. So what's the, let's say, capacity of the machine or system in terms of qubits? That one is not enough for a real estimation what we can achieve with the machine. The second line is talking about the decoherence time. What I mean by that, quantum qubits, comparing to classical bits, if I simplify a bit, they can not only be 0 or 1, but with some probability, they can be 0 and 1, and maybe even a lot of values between it at the same time, with some probability. And that time during which that particle or quantum bit can be in that state is described on the second line. So you see on the superconducting here, we see it's in microseconds, then we see other technologies in milliseconds. Of course, this is 2 years old. Through the time, these technologies are improving. But these are obviously very important parameters. Number of qubits is not enough. And then Microsoft is not only list, but if you follow their announcements, then a few years ago they announced that they also have an intention to build a quantum computer. As of today, they still don't have it. However, they got all the layers already prepared to be used on top of it. So definitely it's interesting and important to watch the space, because in this area of IT, there are new important announcements. I'm not going to say every day, but more frequently than on a monthly basis. I pick up one particular vendor now. A, I'm an ex-IBMer. B, we partner with IBM. C, IBM is really a leader in this technology as of today, at least in terms of the capacity of their systems. What is described here is their publicly available roadmap. So I'm just encouraging you to watch their site for updates. Why I'm showing this one is because people, a majority or a lot of my colleagues in IT in general, they still don't believe that quantum computing is the thing and it will really be successful. So we see what IBM achieved through the years as they were able to tick all the boxes, like we delivered, every year delivered. So if they will continue like this, in a few years, we will be able to see error correction, which is very important because of, as I will show a bit later, current quantum computers are a bit noisy, so they are producing a lot of errors. But with error correction, this can be a major step. And you see here a quite high number of qubits in the chip and quite high number of quantum gates, which I will explain in a minute. What is also worth to mention, besides the real quantum computers, computers based on the real quantum phenomena, we also have quantum simulators. So we can simulate quantum computers on top of classical computers. Here are examples of two options. There is a particular vendor providing access to those systems, with all, including their services and so on and so on. On the left side, we see an open source project from NVIDIA, which could be maybe more attractive because if you got some cards, you can then use this toolkit and simulate quantum computers on those GPUs. I'm afraid the pictures are not visible perfectly, but let me just, this is kind of terminology being used, especially by IBM, where we are already in the quantum utility area, which means if you build your algorithm, it can now run faster on the real quantum computer than on top of any simulator, on top of any HPC cluster available. There is kind of a rule of thumb, or if I should say one number, it's like 100 qubits. Current supercomputers could potentially simulate up to 100 qubits, while IBM is now able to give you an access to the system with 127 logical quantum bits. So we are in this area already. In the future, one day, we will get to quantum advantage, where it will make sense to that the quantum computers will be able to solve those issues which classical will never be able. So let's now summarize slowly where we are in terms. So the term we use is noisy intermediate scale quantum era. Intermediate scale means we are in the hundreds of quantum bits. We don't have available thousands or tens of thousands of them. And the noisy means we got quantum bits which are not perfect. So they cannot stay in that coherent time, in that quantum superposition state for a long time, and they can be distracted. between them or by outside, by vibrations, temperature changes, and so on. So they are quite fragile still. So that's the reason we are not in quantum advantage states yet. However, we still can do a lot of things with quantum computers already today. Of course, we can scare everybody that future quantum computers will break your RSA, so it's time to apply new algorithms for encryption, so-called post-quantum crypto. We can already use algorithms which are available, and maybe it's good time to spend time now with our preparation for the future. So invest in skills, talent building, to become familiar with a bit with the mathematics, which is behind quantum computing, because this one is a bit different than the one behind classical one. And of course, at least in Slovakia, my country of origin, we do a lot of things with quantum communication, comparing to quantum computing, because this is so-called low-hanging fruit. You just need few quantum bits in order to establish quantum communication. So this is all happening now. So let's discuss like what could be your job now around quantum computers, or who can work with quantum computers. So, and how it works. So on hardware level, definitely you need to have a deep knowledge about the particle system and model. So typically these are employees of those hardware vendors who are able to work on the hardware level. I call it hardware, I'm not sure if they call it hardware. So on the very bottom. It's important to mention that we don't have operating system, we don't have middleware. There is nothing like this or native programming languages for quantum computers. So it means we are kind of in back to 50s of the last century with classical computers. So we operate on the bit level, on the quantum bit level. And we build so-called quantum circuits, which we will show you later today. And then talking about quantum computing, it's kind of important to discuss a bit computing versus programming. As I mentioned, we don't have a native language, so I would not call it programming yet. We call it computing. So that means that we still need to learn a bit about how to put the algorithm and all the phenomena and mathematics behind that. By the way, so this is kind of computer science versus quantum information science. Quantum information science is the official name of this new sister or daughter of computer science. So Google this one or ask AI for this term if you'd like to learn more about this. And there is what we call PhD barrier. So typically, as of today, the majority of people working with quantum computers got some education level. And as we know, in order for any technology to be successful, we need to bring it to a wider audience. So we can expect some framework, some new layers to become our friends. So we will be hide from the complexity and those levels. So what could be the use cases? I put some fancy here. I will start from the right. Finance, that sounds good because typically finance means money. And the financial institutions, they like to earn more, but also they need to protect themselves from somebody to attack them and steal their money. So we see that they invest now in some R&D projects, and some of them also implemented first algorithms or programs with quantum computers, as you see around option pricing, credit risk. And on the next slide, I will discuss this a bit more. I think what's important, I believe you are all excited about AI. So there are new areas to be discovered or optimized for AI around quantum kernels and quantum neural networks for AI. And on the left side, as you see, it's about simulating systems which are quantum-based. So a lot of research and science. The next one is more kind of marketing oriented, where in some level, you can fix all the issues in all the areas. However, let's skip a bit those quantum communication and encryption, kind of infrastructure-related benefits from quantum computing. And let's talk that the two main use cases are optimization problems and simulations. And by simulations, not necessarily financial sector, more for scientists. Imagine some research, DNA, biologists, chemistry, all those. So the current computers have limited capability how to represent real data or information about the molecules and so on. They need to cut it. They cannot do it precisely. They can just approximate because they don't have enough capacity. So in the future, we believe quantum computers will be able to fix this. Just for your imagination, imagine that if the quantum bits would be stable and able to keep the state for longer than a few microseconds, with 100 quantum bits, you can put in those bits 2 power 100 classical bits of information, which is quite a lot. It's more than all the data which exists on this planet as of today, at least based on my research. So these are kind of real-life examples. I will just point you to my favorite one, which is MasterCard case, how they use with I believe just with 10 quantum bits, what they can achieve in terms of foreign exchange strategy to make some money if you buy and sell foreign exchange between few different currencies. So I think that's the best one. When you Google it, you will find a lot of videos recorded from different conferences. Yeah, this is the motivation, like it's time to start, because sooner the company would start, they can become pioneers and maybe beat their competition, but this is more business related. So let's now before we will do the live demonstration, so to make it for you at least, so you can digest it, I'll do some small preparation with some basic terms of quantum computing. Before we start, let's go back to the history, because that's an interesting story how quantum computers really started. So as a conceptual idea, they started in 1981, when a famous physicist, Richard Feynman, said what he said. We like to simulate the universe or whatever they need to, whatever they as physicists focus on in their science, they better do it on the computer which is based on those quantum phenomena and not on classical computers. I believe like 17 years later, there was this paper, which is by the way available on the web. This paper was published about which formalized how such a thing like quantum computer should look like, what are the components in terms of hardware and on top of that. And now let's describe very briefly, and I really apologize, I'm not a physicist, so I'm sure I will not be precise enough, but to simplify that, let's just talk about the two, I guess, most important and a must to understand at least till some level quantum phenomena. So on the left side, we've got superposition. So that's the thing that my quantum bit can be 0 and 1 on the same time with a particular probability. I'm always repeating this mantra of probability because quantum world is probability-based, it's not deterministic. So that's the thing why we can have 0 and 1. And on the right side is so-called entanglement, quantum entanglement, where two particles can be magically connected between them. In our case, that would be 2 qubits. And they are, and again, I will simplify, but they are connected by some rule which we can define. And the rule, typical, to make it simple, the rule can be, 2 qubits should have always the same value, or the opposite value. And with entanglement, we can achieve this. And this is now giving us completely different potential comparing to classical computers. Because we can entangle not only 2 qubits, but many qubits between them. Actually, we can kind of encode a rule, some specific rule between qubits. And then my algorithm will not go sequentially like my classical one, where I need to put a data sequentially so it can work with those, but it can do it kind of magically in one shot on top of a lot of data, or a lot of values. Now the terminology, there will be 3 columns. Quantum bit is typically represented for us so we can understand it, because we got some limitations to understand quantum as a vector. So what you see in the middle here, it's called a block sphere. I encourage you to use simulator like this one, which is available on the web page, where you can play with the qubit. So it's a vector. This is important to remember. On the left top, we see that the 0 and 1 representation in terms of a matrix. And on that block sphere, this is a consensus that the north pole is 0 for us, south pole is 1. So that's the qubit. Then we have operations called gates. As we have gates in our classical IT, like AND, OR, NOT, we've got different gates for quantum computing. Again, there is a name of the gate, the graphical interpretation, and a matrix. So it's the second time I'm showing you a matrix, which means that the linear algebra should become your friend. Because to operate an operation on top of a vector is actually multiplication of a vector by a matrix. And those gates, as you can see, some of them are operating on 1 qubit only, but on those qubits which are entangled, we have here 2 qubit gates. And obviously, you can imagine there are also 3 qubit gates. But as you already work with AI, you are not afraid of matrices, I guess. And on the very right side, very important, I'm not sure how visible it is, this is what is called measurement. Because in the end, that quantum bit will give us a result 0 or 1, nothing else. While during computation, it can work with different values, but as an output, after my algorithm run, and I measure the value, it's always binary, 0 or 1. So we are going from the quantum state, superposition state, let's say, to a classical state. And typically, then we store this information in the classical bit. So again, the quantum bit will return me always 0 or 1. Okay. So we have specific gates which will help us to manipulate the bit to a superposition and entangle. That's called Hadamard gate and control knot. And then what we are building actually are quantum circuits. That means on the picture on the left, we have 3 quantum bits called Q0, 1, and 2. And then we have a C3 UC, which means 3 classical bits to store the results. And what we do, this is the graphical representation, we manipulate those bits with the gates. In the middle, there is a description is an example of the code, not necessarily representing what you see on the left, it's a random one, in so-called quantum assembler. So there is a project called openquasm.com, so you can look on that. But majority of people working with quantum now are obviously working with some SDKs, typically in Python. And then you work with Python, but you better know what you do. So you have to understand quantum bits and quantum gates anyhow. And then these are probably the most popular SDKs. Both of them, I believe, are open source. One is basically sponsored and run by IBM, and the other from the company called Pennylay. Okay, so that's an example of Qiskit. So it's SDK, that's important. And obviously, when you put your algorithm there, you can then, let me put it in the old terminology, I can run it against any backend I wish. So that backend could be my local simulator. It can be my simulator in my network on my server. It can be in cloud against whoever is providing quantum computers in the cloud. Or if I'm lucky one, like somebody here in Ostrava, against my own quantum computer. Before I finish and will let Marek to give you the live demo, I like to point to one important fact here. To build an algorithm is maybe even less than a half of the issue with quantum computing. The same issue, if not bigger one, is how to represent real-life data, information, and encode it inside quantum bits. Once I manage this, I'm not going to say easy, but much easier, just to run an algorithm. But the magic is how to encode those data in the quantum bits. Here we go. Marek, the stage is yours.
So, hello, my name is Mark, and my goal is to provide you with a comprehensive explanation about how does quantum computing work and give you some insights into quantum programming. So, as my colleague has already mentioned, the main idea of quantum computing is to take the advantage of quantum phenomena in quantum physics, primarily the superposition and quantum entanglement. Because you see, those quantum particles can exist in multiple quantum states simultaneously, all at once. But when we measure the quantum system, it collapses, and we measure only one possible outcome. But upon the measurement, it is in every possible configuration, every possible combination of states. This quite mysterious nature of quantum particles holds significant potential, as you will see. So researchers have tried to extend this superposition property into more macroscopic objects, resulting in the thought experiment called Schrödinger cat to be created. It was proposed by Erwin Schrödinger, the father of the quantum physics. And in this thought experiment, we consider a quantum particle with a quantum property in superposition, such as the spin of the particle. But we don't measure this property. And based on the value of this property, we decide to take or not take the action, such as releasing or not releasing the poison. But since this quantum property is in superposition, in theory, theoretically speaking, the poison is both released and not released at the same time. Thus, the cat is both alive and dead at the same time. Yeah, but ultimately, it was discovered that we can use this phenomenon to perform calculations, and with remarkable efficiency. So let's take a look at the quantum solution to some problems. But first of all, to fully understand the approach of this quantum algorithm, let me quickly go through some key terms. Standard classical computers use this standard binary encoding that you are probably familiar with, okay, just binary encoding of number. But there is also another lesser known encoding called Fourier basis encoding. This encoding operates like a clock. The first qubit is rotated by half, another by quarter, the third by 1/8, and so on. It's just another type of encoding, okay? And now let me introduce you a first quantum algorithm called quantum Fourier transform. It is being coded in Qiskit, a library in Python. Qiskit is really easy and straightforward way to code and manipulate and create quantum circuit. You can also simulate the quantum computer on your local machine. It's all thanks to Qiskit. Here is a code. I will post this code on my GitHub, but I will explain you visually. So this is called a quantum circuit. and those lines are qubits, and the operations on qubits are performed in the form of these quantum gates, or those controlled quantum gates, meaning that if this qubit is 1, then this gate is applied on this qubit. This whole process is really complicated, and it goes way beyond the scope of this presentation. But to put it simply, this quantum algorithm just transforms this computational, those binary encoding, into this Fourier basis encoding, and vice versa. With that in mind, let me introduce you a solution, a real-life use case, a solution to the subset sum problem. This problem seeks to identify a subset of a list of numbers that sum to a specific value x. We will use the numbers 4, 8, and 6 just for simplicity, okay? And we will try to find which number sums to number 10, okay, just for simplicity. This is the NP problem, meaning that the only possible way to solve this problem is to try and go through every possible combination, and there are lots of combinations. There are 2 to the power of n combinations, which became really impractical and uncountable even for supercomputers. And now let's focus on the quantum approach. I will explain you visually the code. This is how it looks like. Now pay attention. We will divide this quantum circuit into 2 parts. Those qubits will serve as a quantum register, storing the value, the numerical value, and those qubits will serve as a control qubits, meaning that if this first qubit is 1, then the first value will be added to the quantum register, meaning that if this qubit is 1, we will add the number 4 into quantum register. And as well as if this second qubit is 1, then we will add the number 8 into quantum register, okay, and so on. But now, here comes the funny part that quantum computers are capable of. By placing those control qubits in superposition using those gates called Hadamard gates, details doesn't matter, but we can place those control qubits in superposition, meaning that each of these control qubits can represent 0 and 1 simultaneously, all at once. Then this controlled operation is both applied and not applied at the same time, since it is in superposition. Meaning that when we put, for example, this first qubit in superposition, the value 4 is added into quantum register, while also it is not added into quantum register. So the value in this quantum register is in superposition of the value 0 and 4. And this goes on and on. So for example, for this second qubit, if it is in superposition, then this controlled operation is applied and not applied at the same time, meaning we will add the second number, the number 8, into quantum register, while also not add the number into quantum register. That means that after this second part, the value in the quantum register is in the superposition of the values of every possible combination of those 2 numbers. And this goes on, and this scales up exponentially. So, in the end, the value in this quantum register is in a superposition of every possible combination of those numbers. Yeah, and then we will apply inverse of quantum Fourier transform just to make the numbers more readable for human. So, however, here comes a big catch, because like I mentioned earlier, when we measure the quantum system, we destroy it. It collapses, and we measure only one possible outcome. So when we measure the quantum register, we will measure only one possible sum, one possible combination of those numbers. So as you can see here from results, I have run this using Qiskit, simulated quantum computer on my local machine, and those are the results I obtained. So as you can see, we are equally likely to measure any of the possible combination of sum. I have run it 1,000 times, this circuit. However, we can make a little trick, and there are some optimization techniques, some amplitude amplifying techniques, and some constructive and destructive interference techniques which go way beyond the scope of this presentation. But basically, using some techniques, we can manipulate with those probabilities and increase the probability of measuring the desired output, the solution to the problem, and lower the probability of measuring the incorrect, unwanted solutions, outputs. So those techniques are also part of our own research. So using those techniques, we can change the output of our program to this output. So we can amplify the probability of measuring the correct answer to be up to 80% sure that we have obtained the correct answer. And if not, we can run it again. So let's make a comparison. Classical computer goes through every possible combination of those numbers, meaning that it can solve this problem in big O of 2 to the power of n. But quantum computer, since it is in superposition, it can solve this problem in big O of n. Those results are quite groundbreaking because this directly challenges the P versus MP problem. If somebody is familiar with it, we have solved the MP problem in polynomial time, which is one of the Millennium Prize problems. So this holds a significant potential. Furthermore, this subset sum problem is considered as a backbone of lots of other NP-related problems. So when we are able to solve this MP, or this subset sum problem, we are basically able to solve much more another MP problems, which has lots of real-world application. It can solve the traveling salesman problem in polynomial time, the max cut problem. It can really efficiently work with the nodes and in graph theory. So by the way, I have omitted lots of details, lots of important details, just to make it more comprehensive. I didn't mention everything. So it's not completed yet. There are some paradoxes we need to tackle, but as it shows, the quantum computers are really close to solve every NP problem. So this was quite complicated. So if you have any questions, you need to find us somewhere. We will be more than happy to answer you something or explain to you it again. Thank you for your attention, and I will pass my word back to my colleague.
Please, if you can just show those classes as we discuss, and the bit of Python.
Mm-hmm. I will show you a little bit more of the Python code. It is all based on this Qiskit. In this Qiskit library, which provides you with quantum circuit classes and objects, and there are lots of other methods and functions to create, manipulate, configure the quantum circuit. Basically, it's a hybrid approach where classical computer computes the parameters to the quantum gates, and then the quantum computer is executed, the quantum circuit is executed, and it will return the results to quantum computer and to classical computer, sorry. And the classical computer needs to decode the information because it became in with quantum form, so the output needs to be decoded back again to the classical represent of the number. So with that being said, thank you for your attention, and I will pass my word back to my colleague.
And I'll add just one thing to it. Again, this was running in Python on the local computer. All those pictures you saw were generated by that SDK. In other words, you don't need to have an access to the real quantum computer or quantum simulator. You can start today by learning the principles and then using SDK like this one. Yeah, and just to conclude soon, yeah, this is another topic. It's about the building talent. So what we were showcasing here also on our booth was a desktop quantum computer, which is not very high performing. It's with 2 qubits. But with 2 qubits, you can explain all the gates, how to build the circuit and everything like that. So we believe that soon, at least in my country, we will see that in schools, or so we working with some schools to start to have kids to teach not only the classical IT but also quantum. I believe here in Czechia you are even more advanced already, at least in terms of universities. This one is more related to high schools. And I like to also share with you that the UNESCO announced a few months ago that the next year will be named as the International Year of Quantum Science and Technology. So you will see a lot of buzz around, I'm sure. And to conclude this presentation, I like to finish with the words of Charles Henry Bennett, that what we have to all learn is that this world probably operates completely differently than we thought till now. Thank you very much for your attention, and I believe we still have some time for your questions now.
Okay, so we've got 2 questions. First one, what are the chances of quantum becoming a personal computer compared to being streamed data center resources?
So thank you for your question. Basically, we don't know, but we are certain that quantum computers will never replace classical computer because of the way how does the quantum computer work. It can solve problems much faster, but not all of them. Only the small subset of every problem can be solved on quantum computer more efficiently compared to classical computer. The most probable way that will happen in future is that it will cooperate. It will work together. That classical computer will solve its algorithm that it is best, do some calculations, and the problems that are better on quantum computer will be passed on quantum chip, and quantum chip will return those results back to classical computer to process it again. So I hope I answered your question.
And if I may add something, look for the quantum-centric supercomputing. That's the term, 4 letters. Quantum-centric supercomputing. So researchers, people are working on those kind of frameworks, how to integrate quantum into HPC. So the quantum resources will just become a new family of resources available.
Okay, thank you. The next one is, in your company, do you already work on real business cases which would utilize quantum computing? For example, this Qiskit library.
Thank you for the question. That's on me, I guess. Yeah, actually, when we started this story with quantum computing at Arikoma, we decided to do it end of last year, so it's a new story for us starting this year. The plan for this year was to build a team, to do some popularization, evangelism, and so on. But we are faster than our plans, so we have a prospect. It's from finance, and so we don't have any deal, we don't have any real-life project yet. But we have a prospect very much interested in quantum, so we will soon do, let's call it a proof of technology for them. Okay? Which is in a specific case of what I can mention, the credit. It's kind of divided candidates in two categories. Like, I will give them a credit or not. I think that's fair enough. Yeah.
Okay, thank you. Another one. Was this talk in this room or in all the rooms at once?
Of course.
The answer is yes.
What was the question?
Another one. Will be my Windows or Mac OS faster on QC? Like quantum computing.
Your OS, operating system, what was it?
Mac OS, yeah, Windows or Mac OS.
Well, we had the first question about if it will hit the personal computing. I believe while I will be alive, this is difficult to estimate, right? But I don't see it coming on personal computers. However, let's see what happened during the last 2 years with ChatGPT and generative AI itself. Was I dreaming about this 10 years ago? Not even. So, as somebody said before me, it's very difficult to predict, especially the future.
Okay, the last one. From the demo, how to work next with the result if there is only 80% chance it is correct?
Thank you for your question. There is a big problem in quantum computing. It's related to measurement. When we measure the quantum system, we destroy all the information that is in superposition inside it. So we need to run it multiple times to form a statistical mathematics and evaluate what was the best answer. And to do that, you little bit destroy the advantage that you gain at the beginning, that you computed it faster, but you need to run it multiple times. So it balanced. The better approach is to use this superposition as an input to another problem, as an input to another quantum algorithm. And this has a bigger potential. Okay, this is quite beyond the scope of this presentation, of this talk, but you can pass the output of this problem in superposition as an input to another problem, and you will run this another quantum function with every value in this superposition all at once. So that when you stack multiple quantum function parallel, not parallel, serial, then when you run it multiple times to perform statistical evaluation, you still have a solid advantage.
If I may, as usual, add something to this, which will be less technical. Please Google BMW quantum sensors, Atos or Eviden. They did some project, or at least they won some challenge there, which was exactly about this hybrid approach, that with quantum they were able to calculate some stuff much faster in terms of hours instead of terms of weeks and weeks. And then as a post-processing, they just verifying the answer by a classical one. And still it's much more efficient than the original classical only. And then the B is philosophical, if I may. like, this is a business challenge as well. If I'm approaching you, you are the manager who makes the decision, and I tell you that this solution will be giving you answers like, with 85% probability, this is the solution which belongs to the 5 best. Is it good for you or not? Because people still tend, oh, I need 100% all the time. And I think that those times are over now.
Thank you. There is one question in the audience.
Okay, thank you very much. Thank you for your presentation. First of all, I have one remark and one question. One remark, I'm from IT for Innovations, National Supercomputing Center, and I would like to make a promo that we have a simulator running on our big and small cluster on A100 and V100 NVIDIA cards, and we are able to simulate 30 qubits perfectly, which is quite high power. And so this is a promo to any one of you that we are there. Quantum computer at Ostrava will be soon. And my question is, you have here a gate-based programming level. Are you also concentrating on a pulse level?
Pulse level? No. In this quantum programming, you can program low level, like in any classical approach. You can code in assembler, for example. But you never program in respect to the type of processor you are programming on. You write the same code on macOS, on Windows. The same thing is happening right now on quantum computers. There are really high-level gates, which are executed differently on another hardware processes. So in the end, it doesn't matter which technology you run the quantum circuit on, it should be okay.
Yeah, and just to make it clear, like in Qiskit, you have a set of gates available. Let's say there are 15 gates. I made this number up. But in their, let's call it, instruction set of the IBM quantum computer, there are not 15 gates. There are maybe 3 or 4 of them. And then during the process, when I submit my job, I call it the job, it's not job, but I'm a mainframer originally, so sorry. When I submit the task, there is a transpilation process where their part will translate it from my gates to the real gates which exist, and only then the algorithm will run. But I believe for us, we are from business, that would not be very efficient to focus on that low-level programming. I guess we will never be able to do it, as our intention is to build real applications for business.
So when I'm here with the microphone, is there any other question you want to ask? If not, then thank you again. Thank you very much.